All right, everybody. So a couple of last ideas about integrals, double integrals over general regions. So just a few rules that we've seen sort of versions of this for all the different kinds of integrals we've done. So I think we'll go through them pretty quickly, and I think most of them will make pretty intuitive geometric sense. So for instance, let's suppose we were integrating the sum of two functions over a region. Then we can integrate each one individually and add those two together, right? And in fact, we can do plus or minus. Again, as long as they're all integrable and that sort of stuff. And the intuition, of course, is just when we do those estimating, rectangular solids, you're stacking them on top of one another. Or in the case of subtracting, or if it's a negative function, you're putting one and subtracting the height of the other one from it. And so you can think about stacking volumes on top of each other. If you multiply a function by a constant c, that's the same as integrating first. Sorry, if you multiply by a constant c and then integrate, it's the same as integrating first and then multiplying. Again, the same intuition that we've used before. You're stretching or compressing this thing so the volume expands or contracts in the same way. If you've got two functions that have this relationship on D, then the integral of the larger one is going to be larger or equal to the integral of the other one, right? It's a larger volume. And then here, this one takes a little more explanation. So let me write it, and we'll explain what all these symbols mean. If D is equal to the union of D1 and D2, where the intersection of D1 and D2 is the empty set, then the integral, the double integral over D of f dA is equal to, you can take the integral over D1 and then the integral over D2 and add them together. Okay, now let's just draw a picture of what this is. If we're integrating over the region, let's say my region looks something like this. Let's say here's the XY plane, and let's say I have, let's say here's a function, and let's say I have another function. I'll draw it in blue. Let's say we're integrating over this region between these two functions, except only where y is positive. So the place that we're integrating over, right, would be, let's try to draw this, would be this region. Let's say we're ending right here, right? So this is the region we're integrating over, this green region on the interior here. Well, you might want to divide this up because remember, you're going to be bounding y by these, the red and the blue functions, except in the middle, you're bounding y by the red function and the x-axis. So you might decide, in fact, you will need to decide to divide this into two regions. This region here, and then all the rest to the right. This region here. Right? So it's just, and so all that this is saying is if D is the union of D1 and D2, so this whole thing would be D, the entire region we started with. D1 maybe is this, D2 is this pink region. The union just means if you take all the points in D1 and all the points in D2 and consider all of them part of your new set, that's D. And the fact that D1 intersecting with D2 is empty means there's no points in common between these two regions, okay? It's just saying we can do an integral over this part, then the integral over this part. So you can imagine now this is the domain, this is in our xy plane. If there's a surface floating above this, we're just slicing it vertically and getting the volumes of the two separate sections and then putting them together, right? This is very equivalent to, right, you might do a problem in Calc 1 where, you know, you have a function, maybe you want to get the, you have two functions. Let's say you want to get the area underneath the whatever the smaller of the two functions is. So you're trying to do all this area. You'll split this into two integrals, right? One where you integrate under f, the next where you integrate under g, right? Maybe it's going from a to b, and you find a number in the middle and do these two separate integrals. Same idea, you can split up the region that we're talking about. Okay, then finally, one last property. Sometimes this is good for estimating. If my function f is between two numbers, little m and big M, thinking of them in the minimum and the maximum on D, and A of D is equal to the area of D, then, and let me put in one other thing here, this area of D, one way you can figure this out, by the way, is A of D is just integrating over the function 1, right? You're just taking your region and going 1 unit up. You're getting the volume, but the volume will be the area of this times the height, which is just 1. So the volume, other than the units in terms of the number, is going to be the same. So in any event, if we know the area of the region D and we know our function is bound between these two numbers, then we can say that if we take little m times the area of D, that must be less than or equal to the double integral of our function over D, which must be less than or equal to the large m times the area of D, right? So you're getting an upper and lower bound on the size of this integral, right? The comparable idea from single variable calculus is if I have a function f, we're looking between a and b. Well, we can pin it between the area under this curve is going to be between, it's going to be greater than the rectangle whose height is at the lowest value of f, and it's going to be less than the area of the rectangle whose height is the highest value of f, right? We probably wrote something like, if we take m to be the minimum value here and big M to be the maximum value here, then we could say something like m times b minus a, that's the area of the small rectangle, is less than or equal to f of x dx. That's the area under the red curve, which is going to be less than the area of the large rectangle, right? It's the same kind of thing. The picture's just in more dimensions. Let's take a quick look at the picture of this, right? So if we have a function, right? So here's our f of x. Let's say my region is this circle, so you can see it there inside, right? So I'm looking at the piece of the function above that circle, right? Again, there's the region, now the piece of the function. Let's get rid of the function itself. So there's the piece of the function. I'm going to put in the xy plane, so we can see that's a region in the xy plane. Here's our function, the piece of it floating above that. So the volume between that circle in the xy plane and this shell on top of it has to be bound between this this is a cylinder in this case. That just happens to be because the region is circular. But what we see is that if I took the area of that cylinder and the height of this cylinder is the minimum value of this function, that's the volume of that cylinder. So that little m times the area of that circle gives me the volume in this cylinder. Clearly the volume we're looking for is larger than this. And then I can look at a cylinder whose height is at the maximum of this, right? And clearly the volume we want is going to be less than that. And so we've pinned it between these two volumes. So in cases where, for instance, maybe the integral is very difficult or impossible to take, we can still get an estimate. And so if you're the scientist working on a problem that you need just to have a good estimate of something, this is a method we can use, right? This image, I chose a function that has a large variety to make it easier to see, but often these max and min values might be very close. And so our approximation would be a much narrower set of values, right? There's a pretty large difference between these two volumes here. Okay, that is it for this video. Thanks everybody. We'll look at one more way to integrate these in this series of videos where we can switch to polar coordinates. So that's coming up in the next one. Okay, thanks everybody. See you next time.